When we talk about the moon landing, most people imagine a simple journey. A rocket launches, astronauts float toward the moon, and then they land. But here's the truth almost no one realizes. The Apollo mission wasn't just a difficult mission, it was a statistical miracle, a razor-thin line between success and catastrophe, a challenge so absurd that even today's supercomputers would struggle to replicate the exact same trajectory with the same margin of error. Think about it. This was the 1960s, an era when computers were so primitive that a simple smartphone today has millions of times more processing power. Yet somehow, humans engineered a machine capable of crossing 384,000 kilometers of empty, unforgiving vacuum, guided partly by a computer, partly by old-school navigation tools, and partly, believe it or not, by pure human instinct. But here's where the story becomes almost unbelievable. Every single moment of Apollo's journey was a countdown to disaster. The rocket had to withstand vibrations strong enough to tear steel apart. The navigation system had to rely on inertial platforms that drifted millimeters, but millimeters in deep space translate into hundreds of miles. And then there's the fact that the moon isn't a friendly target. It's a moving object, racing around Earth at nearly a kilometer per second. Hitting it isn't like firing a bullet at a stationary wall. It's like firing a bullet from a moving train toward another moving train on the opposite side of the planet, hoping they intersect at the exact same millisecond. Yet, despite every danger, every unknown, every technological limitation, humanity not only attempted this impossible challenge, they succeeded. But why? Because the mission wasn't just about reaching the moon. It was about proving what humans can do when they refuse to accept limitations. And the deeper you look into the science, the more the story transforms from a historical event into something almost mythic. The moon landing wasn't merely an achievement, it was humanity's loudest declaration: we are not trapped on Earth. And that single idea changed everything: our technology, our ambition, our identity. The landing wasn't only about the moon, it was about proving that the impossible, under the right circumstances, becomes possible. But here's the real twist most people never consider. The Apollo missions didn't rely on just one navigation method. They relied on a delicate combination of techniques that spanned centuries of human knowledge. Imagine this: inside the spacecraft that was racing through deep space at thousands of kilometers per hour, there was a tool sailors once used during the age of wooden ships. A sextant, a simple mechanical instrument, and yet it became one of the main backups for one of the most advanced space missions in history. Why? Because space is full of uncertainties. If the main computer glitched, if the inertial system drifted too far, if communication with Earth went silent, the astronauts needed a way to know exactly where they were in the void. The sextant allowed them to measure angles between stars and the horizon of the Earth or the moon. Just think about the poetic absurdity of that. Humans use the same technique ancient explorers used to cross oceans, to cross space. But it goes deeper. The Apollo guidance computer, despite being revolutionary, could only perform a few thousand calculations per second, less than what a digital watch can do today. So engineers had to build algorithms that were unbelievably efficient, optimized to the edge of physical possibility. Every instruction, every line of code had to matter, and astronauts had to trust them with their lives. But here's the fascinating part. All of this resulted in accuracy so sharp, so precise, it still shocks engineers today. They were able to hit their landing point on the moon within a few miles, something that seems supernatural given the tools they had. And what makes it even more unbelievable is that the entire mission depended on timing that had no room for error. If they fired their engines a few seconds too late, they would miss the moon entirely and drift into deep space forever. If they fired them too early, they would smash into the lunar surface. Yet somehow everything worked. Not because the technology was flawless, but because the humans behind it were relentless. They triple-checked everything. They practiced every scenario. They prepared for every failure. The Apollo mission wasn't a triumph of technology, it was a triumph of discipline, precision, and raw human determination. The real miracle wasn't the landing itself, it was that humans created a system so redundantly brilliant that even if half of it failed, the mission could still succeed. And if you think navigation was mind-bending, wait until you understand what keeping humans alive in space actually required. Every breath an astronaut took was the result of engineering so tight that a single malfunction could turn the cabin into a metal coffin. On Earth, oxygen is everywhere. We breathe without thinking. But in space, oxygen becomes one of the most dangerous substances imaginable. If pressure is slightly too high, things explode. If it's slightly too low, humans lose consciousness in seconds. Apollo used pure oxygen atmospheres not because it was ideal, but because it was the only lightweight option. Pure oxygen means fire risk. Pure oxygen means explosive potential, yet they still had to use it. And carbon dioxide, the poison that humans exhale, quickly becomes deadly in enclosed spaces. The spacecraft had to scrub it out using lithium hydroxide canisters. If those failed, the astronauts would die quietly, breath by breath, without even realizing what was happening. And water? Even more complicated. You can't carry tons of water into space. It's too heavy, so Apollo generated water as a byproduct of its fuel cells. That water kept astronauts alive, cooled systems, and powered essential equipment. But here's the insane part. Everything had to be consumable. Nothing could be recycled. Once the water was gone, it was gone. Once the oxygen was used, it was used. Apollo was a race against time, literally. Today we use regenerative systems on the International Space Station to recycle water, air, and heat. But those systems are complex. They break. They require constant maintenance. That's why Apollo didn't use them. They needed reliability, not efficiency. So the astronauts lived inside a machine that was stable but temporary, safe but only for a short window. The clock was always ticking. And here's the detail most people miss. Every system on Apollo had layers of backups because engineers knew failure was inevitable. They didn't hope things wouldn't break. They assumed things would break. And that's why Apollo succeeded. Not because the technology was perfect, but because the people who built it planned for imperfection. They engineered survival into the system itself. And that kind of thinking is why humans reached the moon in the first place. Now let's talk about the evidence, because this is where the story becomes even more astonishing. Many people ask, how do we know the moon landings were real? And the answer is so overwhelming, so multi-layered, so deeply rooted in physics and engineering that the conspiracy theories collapse under their own weight. Start with the photographs. Critics say the images are too perfect, too clear, too well framed. But that's not suspicious, that's engineering. NASA used modified Hasselblad cameras with fixed focus and preset exposure. They practiced for months. They rehearsed taking photos in bulky suits. Of course, the pictures look good. That's the point. Then there's the famous argument about the waving flag, which conspiracy theorists love to use as proof of fakery. But in a vacuum, motion behaves differently. Without air to slow it down, any disturbance, like twisting the pole into the lunar soil, causes the fabric to oscillate for longer. The flag didn't wave because of wind. It waved because of physics. And shadows? The moon isn't a flat parking lot. Uneven terrain bends shadows in strange directions, even with one light source, the sun. You can reproduce the same effect in your backyard on uneven ground, but here's the most unshakable evidence. Cosmic ray hits on the original film. High-energy particles in space leave microscopic tracks when they strike film. These cannot be faked. They cannot be forged. They happen only in space. And then there's the tracking data. Observatories around the world, including in the Soviet Union, tracked Apollo in real time. Amateur radio operators picked up the signals. The time delays matched the moon's distance perfectly. Doppler shifts match the spacecraft's velocity. You cannot fake the physics. You cannot fake the trajectory. But the strongest evidence of all is still sitting on the moon today. Retroreflectors. Observatories fire lasers at them to measure the moon's distance with centimeter precision. And those mirrors could only have been placed by astronauts. All of this forms a mountain of evidence so vast, so undeniable, that the only reasonable conclusion is simple. Humans went to the moon, and the reason it looks unbelievable is because it was unbelievable. But if all of this is true, if humans truly did the impossible, then why haven't we gone back in 50 years? That's the question that keeps people awake at night. And the real answer is far more shocking than any conspiracy theory. It wasn't lack of technology, it wasn't fear, it wasn't difficulty, it was economics. The Apollo program mobilized 400,000 people, engineers, mathematicians, technicians, scientists. Entire factories existed solely to build parts for the Saturn V. Entire industries were created from scratch. When Apollo ended, those factories closed. The tooling was scrapped. The supply chains dissolved. Today, you could not rebuild a Saturn V even if you had the blueprints, because the companies that created the parts no longer exist. The infrastructure is gone. It would be like trying to rebuild a medieval cathedral using only modern apartment building tools. The knowledge is there, but the craftsmanship is lost. And here's the deeper truth. Apollo was never meant to be sustainable. It was a geopolitical sprint, not a long-term strategy. Once the goal was achieved, beat the Soviets to the moon, funding collapsed. Space exploration takes time, patience, and long-term vision. Politics rarely offers that. And while today's rockets are more advanced, they're also more complicated. Apollo used consumable systems because they were simple. Modern missions require regenerative systems because they need to last years, not days. And that adds complexity, adds risk, adds failure points. That's why returning to the moon is harder today, even with better technology, because our goals are bigger. We're not trying to plant a flag and leave. We're trying to build a presence, stay long-term, test systems for Mars, and establish the foundation of a true spacefaring civilization. And that takes more than a rocket. It takes an entire ecosystem. But here's the real twist. Everything we're doing today, from Artemis to SpaceX Starship, is not about repeating Apollo. It's about preparing humanity for something bigger, something permanent, something that will shape the future of our species. Apollo proved we could reach the moon. The next missions will prove we can stay there, and that difference is everything. Now consider this: risk. Risk is the invisible force that shaped Apollo, and it continues to define space exploration today, but in completely different ways. In the 1960s, astronauts were test pilots first, explorers second. They understood danger in a visceral way. They strapped themselves into a 3,000-ton rocket that could explode in seconds. They traveled to the void where a single miscalculation meant permanent exile or death. And they did it with a level of bravery that borders on incomprehensible today. Apollo 1 is the grim reminder: 3 astronauts died in a fire during a ground test. But instead of halting the program indefinitely, NASA learned, adapted, and continued. Today, such a disaster triggers layers upon layers of investigation, legal reviews, safety audits, and political oversight. That risk tolerance is gone. Modern space missions must plan for near zero error, which is noble and necessary, but it dramatically slows progress. And that's exactly why we haven't returned to the moon. The mindset changed. Risk is now a public relations problem as much as a scientific concern. Every launch is scrutinized by billions on social media, every failure magnified, every oversight questioned. Compare that to the 1960s, when the nation collectively decided, almost instinctively, that failure was acceptable if it meant reaching the moon first. The contrast is staggering. The astronauts of Apollo were not reckless. They were prepared, trained, hyper-disciplined, but they were willing to accept a level of risk that today's institutions cannot allow. And that difference is subtle, but crucial. Risk drives innovation. When failure is unacceptable, progress slows. Now consider the implications for Mars, where the stakes are exponentially higher. Travel time alone, 6 to 9 months in deep space, exposes astronauts to radiation levels far beyond anything Apollo faced. Microgravity induces muscle atrophy, bone density loss, and fluid shifts that affect vision. Isolation and confinement for months create psychological pressure unprecedented in human history. And landing on Mars presents engineering challenges orders of magnitude more difficult than the moon. There's no margin for error. Yet paradoxically, the same discipline, ingenuity, and courage that allowed humans to walk on the moon will be required for Mars. The problem is institutional and societal. We have not cultivated the same tolerance for risk, and that's why commercial companies like SpaceX are so critical. They operate differently. Failure is part of the process. Iteration is the culture. Their ability to accept controlled risk might finally push humanity beyond low Earth orbit. In essence, the difference between Apollo and modern exploration isn't technology, it's psychology. How willing are we to gamble lives and resources for a vision decades in the making? And that question alone may determine whether humans remain Earthbound or finally become a multi-planet species. But risk is only half the story. There's another hidden factor: motivation. Apollo succeeded because it was framed as a race, a war for prestige, a geopolitical spectacle that captivated an entire nation. Kennedy didn't say, "We aim to advance science gradually over decades." He said, "We will land a man on the moon before this decade ends." That hard deadline focused every mind, mobilized every resource, and aligned human ambition on an unprecedented scale. The timeline was brutal. In 1961, Americans had barely sent a human into orbit. 8 years later, humans walked on the lunar surface. That's an almost absurd acceleration of technological development. Today, space exploration lacks that existential urgency. NASA and other space agencies have ambitious long-term goals, but without a ticking clock or a competitor to beat, progress is methodical, bureaucratic, and painstakingly slow. This is why China's new lunar ambitions and SpaceX's Mars plans are so fascinating. A new geopolitical competition or even commercial incentives can reignite that sense of urgency. Motivation drives focus, and focus drives innovation. Without it, progress stalls. But here's the deeper insight. Motivation doesn't just impact technology, it changes the culture of possibility. Apollo taught a generation that impossible is relative. Yet, in the decades since, we've internalized caution, comfort, and incrementalism. That's why even with exponentially better technology, we move slower. Human psychology is as much a barrier to space as physics. And speaking of physics, let's talk about energy. The rocket equation doesn't care about ambition. It's ruthless, unforgiving. Chemical rockets require exponentially more fuel to lift more mass. The Saturn V launched 3,000 tons to deliver only 45 tons to the moon. Every extra kilogram of payload demanded dozens of kilograms of fuel. Modern proposals like nuclear thermal propulsion or fusion rockets could radically change this, but political and safety concerns delay adoption. And here's the paradox. We could build safer, faster, cheaper systems, but society isn't willing to accept the same calculated risk that made Apollo possible. In essence, human ambition, political will, and risk tolerance are deeply intertwined. Without all three, technology alone cannot push us to new worlds. Apollo succeeded because it harmonized these forces perfectly. Today, even with advanced AI, robotics, and private enterprise, we struggle to recreate that alignment. And that's why every step toward Mars or a permanent lunar base feels slow, fragile, and extraordinarily difficult. Yet it must happen because the stakes are existential. Human survival, civilization's continuity, and the long-term growth of knowledge depend on our willingness to accept risk, marshal ambition, and navigate physics with skill and foresight. The moon was proof of concept, Mars is proof of commitment. And if we fail there, the consequences are permanent. Now, let's pivot to something that most people overlook. The lunar samples. 842 pounds of rock, dust, and regolith, meticulously collected from multiple Apollo sites, scattered across the moon's highlands and Maria. At first glance, they may seem like geological debris, but in reality, these samples are archives of cosmic history. They tell a story billions of years in the making, a tale of a world exposed to solar wind, cosmic rays, and meteoroid bombardment. Each rock carries isotopic signatures that are impossible to replicate on Earth. Thousands of peer-reviewed studies have confirmed their origin, composition, and age. The diversity between sites is staggering. Highlands rocks differ from Maria basalts. Soil composition varies radically, reflecting local impacts and volcanic history. To fake this diversity, scientists would have had to predict the moon's geology decades before humans even stepped on its surface. The odds of creating such convincing forgeries are not just astronomically low, they are effectively zero. And yet, that is only part of the story. These samples are time capsules. They allow us to study processes that shaped the early solar system, providing insights into planetary formation, asteroid impacts, and even Earth's own history. Every grain of lunar dust is a piece of evidence, a fragment of proof that the moon landings were not only possible, but executed flawlessly. But here's where suspense creeps in. These rocks also hint at challenges we will face in the future. They're harsh, dry, and chemically reactive in ways that complicate long-term habitation. Learning to handle them safely is a preview of what astronauts will encounter on Mars or asteroid colonies. The samples are not trophies, they are warnings and lessons. They whisper secrets about radiation exposure, regolith abrasiveness, and resource extraction that future explorers must heed. And that duality, The wonder of discovery alongside the sobering realization of danger is what makes lunar science so thrilling. Apollo did more than land humans on the moon. It handed us a roadmap, a set of cosmic clues that still guide research, inspire innovation, and tease humanity with glimpses of what lies beyond our planet. Let's delve into the political paradox of space exploration. The moon landings were not purely scientific, they were profoundly political. The Apollo program was a chess move in the Cold War, a way to assert dominance over the Soviet Union. Kennedy understood that beating the Soviets mattered more to the public than collecting rocks or studying lunar geology. But here's the intrigue. Once that political goal was achieved, everything changed. Funding evaporated. Ambitious plans for Apollo 18 through 20 were canceled. The Saturn V production lines were dismantled. Engineers retired, expertise dissipated, and the world collectively exhaled, believing the moon was conquered. The result? Human capability regressed. By the 1980s, we had the shuttle, ingenious, reusable, but incapable of escaping Earth orbit. Low Earth orbit became our playground, but deep space became a distant dream. And that regression was not technological. It was institutional, cultural, and political. We lost momentum, lost focus, lost the ability to sustain the extraordinary. That is a lesson that resonates today. Humanity's ability to reach other worlds depends not just on rockets or propulsion. It depends on collective will, societal alignment, and economic commitment. Without these, even the most advanced technology will gather dust while political priorities shift. Yet, paradoxically, politics remains the driver of the next wave. Commercial companies are rewriting the rules precisely because government programs have slowed. SpaceX, Blue Origin, and others are stepping into the void, bringing risk tolerance, ambition, and speed. But even they are bound by political realities, regulations, international treaties, and public scrutiny. The interplay between politics and technology is a high-stakes dance, a game where missteps can cost billions or lives. And here's the suspense. The next moon or Mars missions are not guaranteed by science. They're contingent on timing, funding, and cultural momentum. The universe doesn't wait, and that is what makes the next decades of exploration simultaneously thrilling and terrifying. Now consider the ultimate challenge: humanity's place in the cosmos. Beyond the moon, beyond Mars, lies the possibility of becoming a true multi-planet species. The Kardashev Scale frames this elegantly. We are type 0.7, barely harnessing planetary energy. Type 1 civilizations control their planet entirely. Type 2 control their star. Type 3 control galaxies. To progress, humanity must expand into space, not for adventure, not for trophies, but for survival. The existential stakes are immense. Earth is a fragile oasis. Climate change, asteroid impacts, supervolcanoes, pandemics, all threaten our survival. Staying on one planet is a gamble with civilization itself. The moon and Mars are stepping stones, not endpoints. Every advancement in space technology, every new rocket, every habitat, every orbital station is an incremental safeguard. They are insurance policies for humanity's longevity. And here's the psychological thrill. The scale is almost incomprehensible. Each mission expands not only our presence, but our understanding, our ingenuity, our ability to survive in hostile environments. Apollo taught us what is possible. Artemis, SpaceX Starship, and future endeavors will teach us how to sustain life beyond Earth. And therein lies the suspense. We are capable of unimaginable feats, yet constrained by bureaucracy, risk aversion, and short-term thinking. The next step requires synchronizing ambition with technology, risk with safety, imagination with practicality. The universe presents no guarantees. One miscalculation could destroy a colony or strand humans indefinitely. Yet the same humans who defied odds to reach the moon are capable of rising to this challenge. History shows that extraordinary ambition coupled with concentrated focus produces miracles. What is terrifying and exhilarating is that we are on the threshold. The moon was a beginning. Mars is the real test. Beyond that lies the solar system, then the stars, and potentially a civilization that spans galaxies. Every decision today, every budget allocation, every rocket design, every international treaty affects the odds of survival. And that is why the story of Apollo is more than history. It is a cautionary tale, a blueprint, a challenge, and an inspiration. Success tomorrow depends on choices today, on whether humanity dares to dream, to take calculated risks, and to commit to the unimaginable. Now imagine standing on the lunar surface, not as an astronaut, but in the mind's eye. The horizon is black, the Earth hangs like a fragile blue marble, and every footstep you take is a defiance of gravity and risk. That perspective, seeing our world from space, changes everything. It alters how we perceive life, civilization, and purpose. This is not abstract, it's tangible. Apollo astronauts described an immediate sense of unity, fragility, and awe. Earth is small, isolated, surrounded by infinite void. Humanity suddenly seems both precious and perilously vulnerable. That perspective alone could have transformed our priorities decades ago, yet it was fleeting. We returned to low Earth orbit, to the space shuttle, to the ISS, circling our planet repeatedly, never leaving its gravitational embrace. The moon became a memory, not a continuous frontier, and that is the tragedy of human progress. We can achieve the impossible, but we often fail to sustain the extraordinary. Yet here's the suspense. The moon is not gone. The clues remain. Apollo artifacts, lunar rovers, and the rocks that silently encode eons of cosmic history. They beckon us to return, to reassert presence, and to expand further. Artemis and private initiatives like SpaceX are not just missions, they are the revival of human audacity. They carry the same spirit that propelled the Saturn V into the sky, yet with far greater technology, better understanding of risks, and a chance to do what Apollo could not: establish a continuous human foothold beyond Earth. But here's the tension. Political will, economic investment, and risk tolerance are still the limiting factors. Unlike Apollo, there is no existential rivalry pushing the timeline. The moon could remain an empty monument for decades if momentum falters, and that is what makes this era fascinating. We are at the precipice, with the ability to recreate history or squander opportunity. Success depends on audacity, coordination, and collective vision. Humanity has already demonstrated that it can defy the impossible, but sustaining that momentum over decades, across bureaucracies and political cycles, is a new kind of challenge. And the question lingers: will we rise to it? Or will the moon once again be an achievement that fades into the memory of a few generations? Now shift focus to Mars. The red planet is a temptation, a challenge far greater than the moon in every conceivable way. Its distance alone, 140 million miles at closest approach, turns every aspect of space travel into a high-stakes gamble. 6 to 9 months of transit in deep space exposes humans to constant radiation from cosmic rays and solar events, which would fry cells, damage DNA, and increase cancer risk. Microgravity weakens muscles and bones. Psychological isolation threatens sanity. And yet, despite these staggering challenges, humanity cannot resist its pull. Mars represents more than a scientific objective. It is a test of our ingenuity, courage, and ability to cooperate over unprecedented scales. Engineers and scientists must solve life support, propulsion, habitat construction, and radiation shielding simultaneously, with no margin for error. Every calculation must be precise, every contingency must be foreseen. The stakes are existential. Failure could mean permanent stranding or death. Yet the audacity is irresistible. That is the human paradox. Fear and ambition coexist, often amplifying each other. And here's the suspense. Success on Mars will not be like Apollo, a brief footprint on alien soil. True success requires sustainability, a permanent presence, the ability to grow food, recycle water, produce energy, and withstand environmental hazards. It is a slow, iterative conquest of a hostile world. SpaceX's Starship and NASA's Artemis-inspired technologies aim to make the moon a proving ground, a laboratory, and a staging point for Mars. But here's the tension. Funding, politics, and societal attention are fickle. If the world's focus shifts, these programs could stall, and another generation may grow up seeing Mars not as a reachable frontier, but as a tantalizing mirage. Yet the scientific payoff is immense. Mars's geology, potential for past life, Water resources and extreme environment teach us about planetary evolution and adaptation. Every mission, even a short robotic or human one, expands knowledge that could be applied to further solar system colonization. The suspense lies not just in the technical difficulty, but in the human dimension. Will society muster courage, resources, and sustained focus to ensure success? Or will Mars remain a story told in dreams and simulations? That uncertainty makes every engineering decision, every launch, and every orbital maneuver feel charged with narrative, suspense, and stakes unmatched by almost any human endeavor. Beyond Mars, the solar system itself presents unimaginable opportunity and equally staggering challenge. The asteroid belt, Jupiter's moons, Saturn's icy satellites, each a world unto itself, rich with resources like water, metals, and organic compounds. These are the raw materials for humanity's expansion, the building blocks for spacecraft, habitats, and sustainable life support systems. But extraction and survival are exponentially more difficult. Radiation near Jupiter is lethal. Extreme cold near Saturn freezes electronics and life alike. Navigation is complex, communication delays stretch to hours, yet the rewards are tantalizing. Mining asteroids could provide rare metals essential for technology. Water ice could be converted into oxygen and fuel. Organic compounds might be the foundation for life support systems in off-world colonies. The challenge is not only technical but strategic. Which resources to exploit first, how to transport them efficiently, and how to survive long enough to establish permanent infrastructure. The suspense is amplified by distance. The farther we go, the longer the time delays, the more irreversible each mistake becomes. Unlike Earth or even the Moon, help cannot arrive quickly. Every mission beyond Mars is a calculated gamble against isolation, radiation, and mechanical failure. Yet history suggests humans will attempt it. The audacity of Apollo, the iterative courage of private companies today, and the inspiration of space as a frontier all combine to make expansion inevitable, assuming we solve logistical, technological, and societal hurdles. And that is the paradox of human exploration. The greater the risk, the more seductive the challenge. And here's the philosophical tension. Why do we push into the void? Not for immediate gain, not for vanity, but for survival, knowledge, and the expansion of possibility itself. These missions are tests of our species, our values, and our willingness to endure hardship for a future that cannot yet be seen. Every step beyond Mars is an experiment in courage, ingenuity, and long-term thinking. Success could redefine civilization, failure could be catastrophic. And that uncertainty, the tension between potential triumph and existential risk, is what makes space exploration the most thrilling human endeavor ever attempted. Now consider the long-term vision, interstellar ambition. The solar system is only a first step. Humanity may eventually aim for other star systems, other planets orbiting other suns, to escape the limits and fragility of Earth. The distances are staggering. Proxima Centauri, the nearest star, is over 4 light-years away. Even traveling at 10% the speed of light, a trip would take decades. Generational ships, suspended animation, or breakthroughs in propulsion such as fusion or antimatter engines are required. Yet the motivation is clear: survival, knowledge, and expansion. The human species has always looked outward, and nothing about our nature suggests we will stop. Here lies the suspense. Interstellar travel challenges not only physics, but our social structures, ethics, and psychology. How do we maintain cohesion over decades-long voyages? How do we ensure skills, knowledge, and culture persist? How do we prevent conflict or disaster in isolated, confined habitats? The technical problems are daunting, but the human factors may be even greater. History shows that our greatest challenges are often cultural rather than technological. Apollo succeeded because society committed, because risk tolerance, motivation, and political will aligned. Interstellar travel will require a similar alignment, but on a scale never attempted. We must cultivate ambition across generations, not years, and manage resources over decades, not months. That is why space exploration is as much a philosophical challenge as an engineering one. It forces us to consider who we are, what we value, and what kind of civilization we aspire to become. And it also contains the ultimate suspense. Will humanity rise to this cosmic challenge or succumb to short-term thinking and self-interest? The answers will determine whether we become a truly spacefaring species or remain a single planet civilization, vulnerable and fragile. Finally, consider this legacy. The moon landings were more than historical events. They were proofs of possibility, tests of human courage, and inspiration for generations. They show what is achievable when vision, resources, and determination align. But the story does not end there. Each mission beyond Earth adds layers to that legacy, building knowledge, inspiring youth, and developing technology that transforms life on Earth. Space exploration is not optional. It is a survival strategy, a driver of innovation, and a crucible for ambition. The suspense now lies in the hands of this generation. Will we reclaim the audacity of Apollo? Will we extend humanity to Mars, to the asteroid belt, to the stars? Every decision, every budget, every scientific discovery shapes that trajectory. Private enterprise is accelerating timelines, but governments, international cooperation, and public imagination remain critical. The universe does not wait. Opportunities are finite. Celestial alignments, funding windows, and technological readiness must converge. And therein lies the ultimate drama. The fate of humanity as a multi-planet species depends not on inevitability, but on courage, foresight, and action. We know the moon is reachable. We know Mars is within grasp. We glimpse the potential of the solar system and the stars. The only remaining question is whether we will act decisively to claim it. History, physics, engineering, psychology all provide clues. Apollo proved the impossible is possible. Artemis Starship and future missions hold the potential to transform that possibility into permanence. The universe is vast, mysterious, and indifferent, but humans have one unique tool: imagination paired with action. The moon landings showed us what imagination can achieve when paired with resolve. The next steps, the moon base, Mars colony, asteroid mining, interstellar ambitions, will determine whether we become the explorers we were born to be or remain bound to a single fragile world. The suspense, curiosity, and challenge continue, not in history books, but in the choices and actions of today. And that is the ultimate lesson. The moon landings were not the climax. They were the opening act in humanity's journey to the stars. Every launch, every discovery, every innovation now carries the weight of that legacy. The universe waits, indifferent but full of possibility. And one day, if we dare, we will reach further, stand taller, and claim the cosmos not as conquerors, but as curious, resilient, and enduring explorers of a vast, beautiful, and infinite universe.